to the poll, you want to make sure that, of course, that's just a sample, so you don't know whether that's true or not. The only thing that you know whether you will be elected or not is after the vote has been cast. So in this case, you want to get the poll and to see whether your support is over 80% or not. So first, this is what you hope, okay? Your support is more than 80%, but you want to know whether that's true or not, right? So then the null hypothesis is this. So basically, if your support is less than 80%, then you want to say, well, that's not possible for you to be elected. So in this case, you want to make sure that it is more than 80%. But somehow, if your support is not enough, you want to say, no, it's not enough, right? So in this case, you draw a diagram. So this is the 80%, okay? Supposedly, that's the status quo, because you want to make sure that whether your support will exceed this number. But when the number is too small, right, then you say, no, you won't be able to get 80% of the support there. So the same thing. And the alpha in this case, okay, is 0.05. So this is the significant level, okay, significance level. So in terms of the standard normal, okay, standard normal, if the alpha, the significant level is 0.05, 5%, corresponding to this significant level, the z here will be 1.64. But of course, this is on the left-hand side, so it is negative, okay? And there's some more information here. We have n is equal to 2,000. In this case, we are talking about sample proportion and population proportion, right? So the distribution is, okay, let us use this number, okay? P will be, okay, the mean will be P, and the variance is PQ divided by N, okay? In this case, we know, because the number is very large, right, is 2,000, much higher than 30, right? Much higher than 30. So we use standard normal. We're going to use normal distribution to deal with this case. So the same thing here. You have to get, okay? You have to get the critical number here. Usually we put it P X star, right? This is the critical value. But because this is a sample proportion, so we use P star, okay? So we use P star here. If the number you get, of course, according to Gallup poll, whatever poll you get, okay, then you get an estimate, okay, the sample value of the proportion of support you get. And then you compare with this critical value. If it is more than this critical value, okay, then what would you say? You say, we accept H naught, okay? But suppose it's less than this critical value, then what you say? You say, we accept H1, okay? So there are two actions here. And of course here it is 1 minus alpha, right? And this part is alpha, okay? So basically, let us just follow through all the example here, okay? So basically, let us check what's the x bar 0 or the p0 there. Okay, let me check where is it. According to the book said this number is 1.65, okay? 1.65. As a matter of fact, if you check the table, it's something like 1.645. So anyway, oftentimes we use this one, but the book said it is this. the difference is very small. Okay, so in this case, they get a poll, and found out that they make a survey, found out that the P is equal to 0.775, okay? So now we want to figure out whether this one is less than the critical value or not. So let us try to find out what's the critical value, okay? We want to know what's the critical value there. So that would be, okay, P star, okay, that is the critical value, right? Minus 0.8, okay? And divided by 0.8, 0.2, 2000. And it should be equal to negative 1.64. So let us use 1.64. Anyone got a calculator? Anyone got a calculator? So please help me with this calculation. So P star, okay, will be equal to minus 0.8 negative 1.64 times, this one should be 0.16 divided by 2000. Okay? Can anyone get this number for me? 0.16 divided by 2000 and square root of it. So what do you get? How much is it? .115. Okay, but this is negative, right? So P star minus 0.8. Oh, 0.015. Okay. So then what is P star? P star should be equal to 0.785, right? Okay. So because P star is the critical value, right? And here we get P star is equal to 0.785. Okay? Here it is 0.785. According to the poll, what do you get? You get 0.775. So in this case, what should you believe? Because the P there, this is the P that you get, right? We say P naught, okay? It is equal to 0.775. It is smaller than this one, right? Smaller than this one. So what does that mean? That means if indeed your support is more than 80%, then for this to happen, for this sample value to happen should be very small, right? So in this case, because it is to the left of the critical value, so what would you say? You would say, no, your support is less than 80%, okay? So in this case, what's the chance that he's gonna be elected? Very small, right? Okay. So basically, for hypothesis testing, it's quite routine, okay? The first is you get to know, okay, what is the people's concern. Now his concern, his support is less than 80%, right? So this one is the alternative hypothesis. After you set the alternative hypothesis, then you know the null hypothesis, and then you get a significance level, okay? You get a significance level. But suppose you don't want to get a significance level, what can you do? You can use p-value method, right? You can use p-value, okay? Anyway, after you determine a significance level and you know this is a proportion, right? So you use sample proportion to test it. And then you try to figure out what is the critical value. And then compare the critical value to the sample value you get. And then make a decision. So there are basically 5 steps here. Okay, so you just follow these 5 steps, you should be able to get it. Any questions? Let us turn to page 364. Okay, let's turn to page 364. We're going to get another example here. And in this case, we are talking about type 2 error, okay? Just try to refresh your mind. If H0 is true and H1 is true, right? If H0 is true and you believe you take action A0, and A0 is that H0 is true, so that's a correct decision. The probability is 1 minus alpha. And if H0 is true and you take action A1 is you believe H1 is true. So in this case, that's an error, right? So this is type 1 error, it is alpha. If H1 is true and you believe H0 is true, that's wrong, okay? Another incorrect decision. And this error is called type 2 error, and that is beta. And here it is 1 minus beta. Okay, let's look at this question. Say, you know, basically you want to know something about these tires, okay? So let us look at the paragraph, okay, the third paragraph. So to illustrate the computation of beta, suppose a manufacturer purchases steel bars, okay, steel bars, and to make cotter pins. Past experience indicates that the mean tensile strength of all incoming shipments is 10,000 psi, and that the standard deviation is 400. Okay, so basically, let us put down the information here. So what's the information we have? We have mu x is equal to 10,000, and sigma x, that's the standard deviation, is 400. Okay? So basically, this is what it is. So of course, we want to make a decision, right, to know whether we want to accept this shipment or not. So what are the conditions? So the next paragraph says that in order to make a decision about incoming shipments of steel bars, the manufacturer set up his rule for the quality control, okay, the quality control. And what are the rules? Take a sample of 100 bars, right? If you take a sample of 100 bars, that means the sample size is equal to 100, right? And in this case, because the sample size is very large, so what kind of distribution we should use? We should use normal distribution because the sample size is larger than 30. Okay, and what's the condition we will take it? Because a steel bar, okay, is to fit into some kind of machines or components, so we know it cannot be too long, cannot be too short, or the strength may not be too strong or too weak. So in this case, the decision rule is that if the steel bar that we get is between 9922 psi and 10,078 psi, then we will take it as good steel bars, okay? So first you want to be able to, okay, draw a picture of all this. If H0 is true, right, that means the mean, okay, is 10,000. Under what conditions will it be taken as good shipments? It will be between 9922 and 10,078. So here, let us say 10,078, and this is 9922. Okay. So in this case, we don't have any information on significant level, right? What is alpha? But alpha should be easy to get, right? Because we have this we have this number. So we should be able to find out a corresponding z, right? So how to get the corresponding z? Then, in this case, what do we get? We get 10,078 minus 10,000, right? Okay. Basically, what we want to find out, we want to find out z, and z is equal to x minus mu, okay, and divided by sigma x, right? But of course, when you use the x bar, right? If we use x bar, then it is x bar minus mu, okay, and sigma x squared divided by n, right? Okay, so basically this one gonna be, because we know sigma x is equal to 400, right? So sigma x squared should be equal to 160,000 and divided by 100, right? Okay, and so that would be 78, okay? And here, what is this? We have this, right? Should be equal to 40, right? So it is equal to 1.95, right? 1.95. So actually, this is close to 1.95, okay? And this is 1.95. Do I get it right? I think that's right? But the book said it's 1.96, so what's wrong here? I think there's something wrong in the book. Can you check with your calculator? 78 divided by 40. How'd you get? You know, just this part. Okay. So actually the book had done something wrong. So in this case, the alpha, okay, should be equal to 0.05. So here is 0.025 and here is 0.025. So the significant level, okay, should be equal to 5%, okay, close to it. Because if you check the table, it should be something like 1.96 and negative 1.96. But here, in this case, it's 1.95, but still is close to this number. So anyway, okay, so basically, if this is the case, then it is done, right? The question is not about how to test whether you're going to take it or not. The question is about the type 2 error. So in this case, we want to calculate beta, okay? So the information we have is, suppose, okay, suppose if mu x is actually 9900, so it's 9,900, okay? Suppose the true value is 9,900, then what is beta, okay? This is the question. So we know here it is alpha over 2, right? And here is also alpha over 2, right? And in this case, H1 is actually 9,900. So in this case, what you're going to say? Of course, if you look at this table, if you look at this diagram, you know this is a two-tailed test, right? If it is two-tailed test, then how to put down the null hypothesis and alternative hypothesis? It should be H naught is that mu x equal to 10,000, okay? And H1 mu x not equal to 10,000, right? And now we have information that actually the mean is 9,900. So we want to put down here, right? So when you draw a picture, you want to make sure that it's corresponding to what's going on here. Because 9922 is here. So 9900 should be somewhere around here. So 9900, right? And the same thing, okay? So now the first thing you want to know is where is alpha and where is beta, right? So we know this is 1/2. So in this case, you want to take action A1, take action A0, take action A0, take action A1. So in this case, the area between here is 1 minus alpha, right? And if you check the table, 1 minus alpha from here should be corresponding to beta, right? So this area should be beta, right? And so this area to the right, so that is 9922 to the right, that is beta, right? And then to the left, that will be 1 minus beta. But there's one question here. If you look at this table, right, okay, because this area, okay, from here to here, that is 1 minus alpha, right? So this area is 1, I mean, on the top, that is 1 minus alpha. Then at the bottom, it should be beta, right? But there is also this area, right? This area to the right should be 1 minus beta, okay? So you have two areas that is 1 minus beta, this area and this area. But of course, it should be, say, this area, the size is A, and this area, the size is B, right? So then A plus B, these two areas is equal to 1 minus beta. But one question here is, because from this on, you know that this area is already very, very small, right? So it is actually close to 0, so you can forget about it basically, okay? So then basically, if you calculate this area, then it is 1 minus beta, and the other area, that would be just beta. Of course, it includes this area too, but it's just 2 further right, okay? 2 further right, and the area is basically nothing, okay? The area is equal to 0. So let us calculate what is the 1 minus beta, okay? What is 1 minus beta? Or we can just say what is beta. That will be the same thing. So beta will be equal to the beta is equal to probability of x greater than 9922, right? Okay? And so that will be, we want to turn x into z. So that will be z greater than 9922 minus 9900. Okay? In the first case, we use 10,000 as the mu x. Okay? In the first case, we use 10,000. Why do we use 9900 now? Because we say, now this one is true, right? Now we say this one is true, so when you calculate beta, you don't use 10,000, you use 9900. So that is here. The same thing, we have the, it is 1600, right? And then it is equal to, sample size is equal to 100, is that right? Okay, so anyway, I can't quite remember what's going on here. I think this is right? Okay. So then this is PZ greater than 22 divided by 40, right? And so that would be PZ greater than 0.55, okay? Can anyone check the table, tell me what is the value of Z greater than 0.55? How much is it? Already? Are you sure? The probability is 0.55? I don't think so. I mean, this value is 0.55, right? But now we want to find out the probability. What is the probability that z is greater than 0.55? You need to check the table, right? So table, what will table tell us? So we're going to check the normal distribution, right? So normal distribution 0.55 is equal to 0.088, okay? 0.2088. So then what's the probability? It should be 0.5 minus 0.2088, right? Because it is this area and above. And the table tells us, okay? The table tells us this area is 0.2088, right? This area is 0.2088. So this area to the right should be 0.5 minus this. So it is 0.2912, okay? So the beta, so in this case, alpha is equal to 0.05. But what about beta? Beta is very big, okay? So the type 1 error is small, but what about type 2 error? Is very, very big, okay? Any questions? So let us get to another example. The question says that, what's the page that I just mentioned? 364, is that right? The questions has another example, okay? The question has another, okay, is here. The second question is that, suppose, okay, mu is equal to 10, suppose h1, the mu, okay, the mu x is equal to 10120, then what is beta, okay? So let us draw the picture again. The same thing, okay, we have this is 10,078, and this is 9922, and this is 10,000. Okay. And now suppose the true value is 10,120. Okay. Here is 1 minus alpha, alpha over 2, alpha over 2, right? And suppose the mean is really here. Okay, so 1 minus alpha should be corresponding to beta here, right? And then here it will be 1 minus beta. So from this value to the right, you take action A1. From this value to the left, you take action A0. The same thing here. From this value to the left, you take action A1. And here you take action A0. Of course, this part should be counted too, right? But as you may know, it's already to the very end of this distribution, so the value is close to 0, okay? So then you can forget about it. And here is 10,120, okay? And here is 10,078, okay? 10,078. So basically the same thing. You want to calculate beta, right? Okay, so let me use this part. So the same thing here, we want to calculate beta, and beta is actually P of x less than 10,078. Okay. The same thing, you want to transform x into z, right? So P z less than 10,078 minus 10,120. The same thing. Here we don't use 10,000, right? Because now it is H1 is true. If H1 is true, then you use H1 here, okay? The same thing, divided by 40. So P, okay, Z less than but this one is negative, okay? So it means P less than negative 1.05, okay? So from here, then you can start to check the table again and to figure out. So this should be, okay, 0.5 minus P of Z between 0 and 1.05. So then you should be able to get a number and find out the corresponding data. Okay, let's take a break. Discussion of ANOVA. ANOVA is analysis of variance. This kind of analysis, this kind of theory has been widely used in the agricultural sectors, okay? People want to test fertilizer or seeds, okay? What kind of fertilizer or seeds, whether they are effective or not. And of course, in this case, we will test several components. And let us use a simpler example. Let us say we have our machines. So we have one factory, and this factory, they use our machines, okay? Of course, there are more than two, okay? In this case, there are more than two. Suppose there is only one machine, it's just easy. We will get samples from it and to determine what kind of distribution that is, okay? And if we have two machines, of course, in this case, we may be concerned whether these two machines are the same or not, because in terms of a company, we are concerned about the quality of the product. And we want to make sure that because there are two machines, we want to make sure that the products out of these two machines are basically the same or acceptable to customers. And if there are just only two machines, that is easy because we can use test hypothesis, right? Hypothesis testing will be enough to determine whether these two machines, the products are of the same quality or not. But now we have our machines. So let us say we have three machines. And three machines, they produce, of course, on their own, right? I mean, in this case, you're going to get three different machines producing, even though they are the same products, but they are coming out of three different machines. And we want to make sure that these products are of the same quality. So in this case, then what should we do? So we say we have one machine, two machines, and three machines. And we have the quality of the first machine, we say the average is mu1. And the average quality of the second machine is mu2. And then for the third machine, it is mu3. So in this case, if we want to make sure that whether these two machines are the same or not, at least we have to do two hypotheses testing. The first one is null hypothesis, mu1 is equal to mu2, right? But of course, that may not be true, right? And then another one, mu2 and mu3, right? If this one is true and this one is true, basically you are done, right? But suppose this one is true, but this one is not true, then you have to do another test, okay? You have to test H naught, mu1 and mu3, right? To test whether they are equal to each other or not, okay? And let us say the significant level is 5%, so alpha is equal to 5%. So that means confidence level is 0.95, right? 95%. So when you do 3 tests, okay, when you do 3 tests, if you want to make sure that actually mu1 is equal to mu2 and is equal to mu3, the best case is for all 3 hypothesis tests, you accept null hypothesis each of them, right? But then there is something changing here, because originally you said the confidence level is 95%, right? This is the original confidence interval, confidence level. So for this to happen, the probability is 95%, right? For this to happen, the same thing, it is 95%. Again, for this to happen, the probability is 95%. Individually, the confidence interval, the confidence level is 95%. But if you want the 3 things to happen together, what is the probability? The probability is actually 0.95 to 3's power, right? Because you have to have them happen at the same time. And these 3 things, basically, the 3 events, as we assume, they should be independent, right? And if you want these 3 independent events to occur at the same time, then the probability is 0.95 to 3's power. So it is not equal to 95% anymore, right? So basically, of course we know what's going on here, but we want to make sure the probability of these events to happen will be the same thing. And if you have 3 hypothesis tests, this will exaggerate, okay, your confidence level, because it's no longer 95%, it is this number. So because of this kind of concern, so we use a different approach, and that approach is ANOVA, okay? So basically this is what's going on, why we have to use a different approach to test whether the mean of several small populations, whether they are equal to each other or not. That is the basic reason, okay? And now let's get to further details. So what are the population, okay? So what's going on in terms of this factory? We say this factory has R machines, and for each machine they produce different products, okay? A different number of products. So first we have I means machine. So you have from the first machine to the R's machine. So the number of I is from 1 to R, okay? And then what is J? When we talk about J, we are talking about individual machine. So for these machines, what do they produce? They produce 1 product, 2 product, and 2 Ni's product, okay? So when we talk about this population, what's going on there? So then we have the first machine, right? And how to denote the data, okay? I mean the numbers, okay, whatever samples in this case. So then you have, usually we use X to denote the sample or the population, right? I mean the individual data. So this is the first machine. The first number, okay, so this number means machine. So this is the first machine. Okay, the first machine and the first product. So X11, it means the first product produced by the first machine. Okay? And this is the second product produced by the first machine. And then this is the N1's product produced by the first machine. Okay? So the first number means machine. The second number means the numbers of product produced by this machine. So X11 is the first product produced by the first machine. X12 is the second product produced by the first machine. And this is the N1's product produced by the first machine. Okay? Then 2. So we finished machine 1, right? Now we are going to talk about machine 2. Okay? The second machine. So this is produced by second machine. The first one produced by second machine. The second one produced by the second machine. And the N2 one produced by the second machine. The reason we use N1, N2 is because we know the numbers of products produced by each machine may not be the same, right? Just as the example say, we use NX and NY, right? Because the number of sample from X may not be the same as the number from NY. Okay, so that's the reason we use this. And we use N1, N2, etc. Of course, the same thing, and then let us say R machine, right? X, the R's machine, the first product, right? The first product produced by the R's machine, and the second product by the R's machine. And here you have R's machine and the R's product. Okay? Any questions so far? Okay. Now we want to know how many samples do we have, or how many numbers, okay, or products in this population. So in this case, we know we have N1 plus N2 plus NR, right? And the total is N, okay? So what's the total number of products in this case? It is summation N I. I is equal to from 1 to R, right? And then this is the number N. So any questions so far? Okay. Then of course, if you look at the first machine, right, you have the mean from the first machine, so we say mean 1, right? And we have the mean from the second machine, we have mean mu2, or mu1, mu2. And then this is the mu r, okay? So basically you have to get yourself familiar with all these symbols, okay? These notations are very important. Okay, then what's the next one? Because you have population mean, then you have sample mean, right? So you have x bar 1, and you have x bar 2, and then you have x bar r. Okay? Any questions? So now the next step is, okay, we have a mu, right? This mu is the whole thing, okay? This mu is the whole thing. So mu1, okay, mu1 is only for the first machine, right? Mu2 only for the second machine. Mu r for the R's machine. Now we are talking about mu. This mu is for the whole thing. According to the first 2 weeks we talk about mu, right? What's mu? Mu is 1 over n divided by, summation of xi, right? I is equal to from 1 to n and divided by n, right? This is the whole thing, okay? The mu, the average, the mean. But now it is a different case, right? Because we have so many machines and so many products for each machine. So how to deal with it? So basically, let us talk about individual machine first, okay? Let us talk about individual machine. So for this machine, for any individual machine, so this may be 1, 2, 3, 4, 5, right? to R. And it should be 1 over Ni, right? Because for each machine, we have, for the first machine, we have N1, N2, and for machine I, we have Ni, right? Okay? And then Xj. And J should be equal to from 1 to Ni. Okay? So you compare this formula and this formula, right? So what do you get? This one talk about we have x1, x2 to xn. And then divided by n, then we get the mu here, okay, the mu here. But now, because we are talking about something a little bit more complicated, we have several small population. The whole population, we have our machine. And for each individual machine, we have this, okay? And so now, we are closer to getting the mean for the whole population. Okay, so this is for individual machine, the mean for individual machine. And now we are talking about the mean, okay, the mu for the whole population. So what should that be? Because we know how many data do we have? I mean, how many individual items do we have? We have n, right? So it should be 1 divided by n, okay? This is from I's machine, right? From the first one to the Ni one. How many machines do we have? I from 1 to R, right? Here, I machine we have from 1 to R. J for each individual product under each individual machine is 1 to Ni, right? So then it should be something like this. Because here we only talk about one I, right? Any given I. But it should be from 1 to R, okay? So here, I is equal to from 1 to R. But then for each machine, how many products do you have for each machine? It is from 1 to Ni. Okay? These are very important notations. You want to get yourself familiar with this. Okay? Any questions? Okay, so this is what we have. Basically, we just introduce the notations here. You want to get yourself familiar with this, and then we want to get down to details, because here we are talking about analysis of variance. So that means we want to know what's the difference there. And in this case, the difference is we want to make sure that, suppose we have 3 machines, we want to make sure that these 3 things are equal to each other. We want to make sure that the machines we have produce the same quality products, okay? Any questions? Okay. Because we want to know whether these machines can produce products of the same quality or not. But we won't be able to do a census for all the population. So what we do, as a matter of fact, of course, we will get one sample out of the population, right? So we take individual product out. And in this case, we denote it by Xij, because it may be a different machine, right? And a certain product from this machine, okay? We get this sample out, and we compare that with the population mean, okay? So minus this. Of course, it may be the same, it may be different, right? Okay? Of course, if it is the same, that gives us some confidence that these may be the same. But of course, it may be different, right? Of course, in this case, it is also a hypothesis test, but what should be the null hypothesis and the alternative hypothesis? So let me put down here, okay? the machines produce so basically what this means is that mu1, mu2, mu3, mu-r, okay? And then H1, if you want to reject this one, okay? If we want to reject this hypothesis, the only thing you need is that sum of the products I think some of the products by some machines. Let me put it this way, okay? So some of the products of some of the machines are of different quality. So what does this mean? Okay, if this is true, right? Mu1, mu2, mu-r. If you want to say this is not true, okay? If you want to say this is not true, you only need one to be unequal. Okay? So if you say all of the machine, and if you want to say this is all of are true, okay? All of this machine, okay, all of and something are true, right? Then you need to, if you want to reject this hypothesis, you only need this, sum of are false. If you want to reject this, you don't need to have all of them are false. You don't need that. As long as one is false, then you reject this hypothesis. So when you accept no hypothesis, okay, if you accept this, it has to be true that all of them are equal to each other, okay? But if you say this is not true, you only need some of them. Say, if you found out that mu1 is not equal to mu2, then this one is false. You don't need to have all of them are false, okay, are not equal to get a false statement on this, okay? According to logics, you only need one. As long as one of them is not true, okay, then are not equal to each other, then this is false, okay? Anyway, let us try to figure out the difference between this individual sample and the population mean. Actually, there are two items, okay? They can be divided into two components, and let us try to figure out what is going on there, okay? So this one, xij minus mu, that is total deviation. Okay? So this one may be different from the population mean, right? And so this is what we call total deviation. But the total deviation here actually comes from two components. The first one is error due to random factors, okay? And the second one is due to the actual machine, so that's factors. So anyway, let us try to get to this, okay? Xij minus mu I, so this is deviation due to error. So this actually occurs randomly because we are talking about the difference. This is the ice machine, right? This is the ice machine. And this is the product from the ice machine. So we are looking within the machine. Okay, we are looking within the machine. So if we are looking within the machine, it is produced by the same machine, right? So if there is anything anything deviate from the mean, what does that say? That says that it is due to a random factor. Okay, random factor is due to probability. Okay, it's not something we can explain because actually we know that's from the same machine, right? If the products are from the same machine, supposedly they should be equal to each other. I mean the quality. But if there is anything different from that, it is something we say due to error, due to probability. Okay, so that is something we are not able to explain. And another component is, okay, mu I minus mu. Okay, so this is deviation due to factor. Okay, in this one, we are looking within the same machine. But for this one, we are looking at across the machine, right? So we are looking at, say, machine 1 and the whole population, machine 2 and the whole population, etc. So in this case, if there is any difference, if there's any difference there, what does that mean? That means actually the machine are not the same. Okay? If there is any difference there, that means the machine are not the same. And if there's any difference here, we know that's due to probability because it comes from the same machine. Okay? But somehow there's still a difference, and then that is something we are not able to explain because we know that's from the same machine. If there's anything different, it should be due to some kind of probability error there. Okay? So the total deviation actually can be divided into two parts. The first part is due to error. Okay? So this is due to probability. Okay? And here that's due to factor. So indeed, the machine is different. Okay? The machines are different. Okay? So let me go further to get to the formula here. So we can put down this xij minus mu is equal to xij minus mu I plus mu I minus mu. So basically, this one is here, right? And this one is the error due, the deviation due to error. And this one is deviation due to factor. And if you look at this one and this one cancel out, right? So what do you get? You get this one. So this is the total deviation can be divided into two parts. The first one, deviation due to error. The second one, deviation due to factor. Okay? But the same thing, if you add all these things together, supposedly you should get 0, right? So the way we're going to deal with it to square it, okay, we want to square it. Okay, so we have square this. Let us first use the summation notation. Okay, let us use I think let's do the whole thing together. First one, we want to square them. Okay, the first thing is we want to square them. The second thing is that because in this case we are only looking at one item, right? We are only looking at one item. But of course, we want to look at the whole population, right? The whole thing. So let us try to deal with from here. So because we are looking at the whole thing, we are looking at the first machine to the rth machine, right? And for any machine, we are looking at from 1 to ni. Okay? And so you have xij minus mu squared And then summation, right? I from 1 to R, J from 1 to Ni, okay? And then you have Xij minus mu I plus mu I minus mu square. Any questions so far? Okay.